Hello everyone, and welcome back to another GIS mathematics lecture video. And in this lecture video, I want to begin to derive some of the common equations that are used in some basic map projections, so you can get a feel for how and why things do what they do. And so before we do that though, I want to talk about two key components of a globe. Of the reference globe, I should say. Two key components of the reference globe. Now this may be something that you've heard before, and maybe something that it's hopefully something that you've seen and just never really consciously thought of, right? But there are two key things with all globes, including the Earth. The first is that parallels, right, intersect meridians at right angles. Right, so put another way, right, we have our parallels running like this. We have our meridians running like this. Actually, let's do that in different colors. Right, so we have our parallels, right, running in red like that around the globe. And then we have our, let's use blue. We have our meridians running north-south like that around the globe. And wherever they intersect, right, they always intersect at a right angle. That's one property. The second property is that meridians converge at the poles. Let me try and make that a little cleaner. Converge at the poles. Right, so if this is the North Pole, this is the South Pole, right? Meridians go like this. Kind of like if you've ever seen one of those striped beach balls or a hot air balloon, right? The lines that run north-south always start at the bottom, and they wrap, and then they converge at the top. Whereas the meridians, sorry, not the meridians, whereas the parallels, right, they wrap around the world like this. So they don't converge, right? They're evenly spaced. But the meridians converge at the poles. And again, this is always going to be at right angles. Okay? So these two facts, unfortunately, with a map projection, right, these two facts really can't be true at the same time. Right? If we make the parallels intersect at right angles, then the meridians won't converge at the poles. So hopefully that makes sense. So let's talk about the first type of map projection that focuses on keeping these right angles and basically makes the distance between the parallels stay constant, which they should, but the distance between the meridians also stay constant, even though, as you can see here, right, the distance here is going to be different from the distance here. It's going to be different from the distance here. Right? But in the first projection we're going to talk about, right, distance is preserved north-south. So the first map projection we're going to talk about, right, preserves distance. Make my handwriting a little bit cleaner, right, preserves distance north-south. Right? And so if you remember in our previous video when we talked about that triangle ABC, right, we said that AB, right, that was that north-south distance. So we already know, right, that our lambda, or should I say our northing, right, our north-south coordinate, where we already know that that's simply just going to be r, which is the radius of our reference globe, times lambda, which is our sorry, theta, not lambda, I am sorry, our theta, which is our latitude. Right? We've already discovered this. Right? But if we want to preserve the distance at the equator, right, at the equator, which is the standard line for this particular projection, right? We're assuming that it's the cylinder wrapped around the equator. Right? We're going to assume that our easting of any given point is simply going to be our r times our lambda, which is our longitude. So let's just really quickly diagram what this means, sort of to recap what we've talked about. Okay, so if we have a point here, N, O, and E, and this is our point A here. We're saying the length going from the equator north or south is going to be equal to the radius, which we know is the radius of the Earth, times this angle right here, which we know is going to be our longitude. So we're saying this is going to be our, so this is our northing. Right, and we can do the same thing for easting, where we would just be simply going the radius of the Earth times the longitude that we were given. Right, so this preserves distance north-south, and we'll talk about transverse cylinders, where again, transverse was where we rotated the cylinder 90 degrees, so that would actually preserve distance east-west. Okay? And again, the standard line being the point where we touch it, and then we can imagine that would get we would get more error as we go along. But hopefully that makes sense. And again, if you have any questions, please reach out. Thank you.